All right, guys. Now we focus a little bit on IKE protocol, what IKE can do for us. And as you can see in these bullets, IKE basically provides mutual authentication between the parties, between the two devices on the tunnel, or between the two devices negotiating IPSec. It's going to first create an IKE security association. Sometimes that was referred to phase one security association. And it's going to start sharing secret information to create the keys that we're going to use later on. Optionally, we can negotiate compression. So IKE not only can negotiate an IPsec session for encryption, but can also negotiate IP compression, to basically save bandwidth if you need to. And finally, it's going to help us on the exchanges to establish a second security association that is called the child security association for ESP or authentication header, depending on what IPsec protocol we're talking about. We're going to go a little bit further or deeper into the security associations, but for now, just think about parameters that we're going to negotiate for our encryption and our security. So these are more details about that first security association, those first messages that are exchanged between the IKE peers. This is called the IKE SA init. So first we negotiate the cryptographic algorithms that we're going to use. We exchange these nonces. Those are basically information that is only going to be sent once and once for all. So the idea is that it cannot be repeated, to make sure that those keys that we are going to elaborate from that information are going to be unique. And then we also discuss or we exchange that Diffie-Hellman group numbers that are going to help us create a secure key based on insecure information. So the point is that we are exchanged. So we still, at this point, we still didn't encrypt anything. We're sending information in clear text, but with that information, we can leverage that information, and we're going to discuss a little bit about Diffie-Hellman later. We can use the Diffie-Hellman algorithm to create a secure key from after exchanging insecure information. So that's kind of the magic of the Diffie-Hellman and the IKE negotiation. With all of that information, we end up creating this, what is called this S key seed, right? Like a primary key, and then we're gonna derive different keys from that SK seed, right? So you see, we're gonna have one that is called SKE. So it's gonna be derived from encryption, the following messages. Then SKA, we're gonna use that for authentication and integrity protection. So to sign our messages, and then we're gonna also use this SKD, to derive key material for our second security association, the IPsec child security association. And finally, for now, we have our second exchange for IKE, which is called the IKEv, right? In this case, this exchange of messages are gonna authenticate previous messages, right? So now we have keys, and if those keys have been exchanged correctly, we can now, authenticate our peers. We're gonna transmit our identity, so information, to make sure that we have everything that we need. And finally, really end up setting up that child ESP or AH security association. And as you see here, all those messages now are gonna be encrypted, using those keys that we created from the first exchange, that IKE SA init message exchanges. So, by the way, and here's another footnote. Let's say this is the whole point of IKE, right? To create those secure keys for our IPsec transform set and that child security association. So the point here is that we need a way to exchange those keys securely, and IKE is basically doing that for us. Um, Finally, right, we have that create child security association exchange, which is going to be, again, to create new child security associations and rekey both IKE and child security associations when we need to. Okay.